Hi guys, today in this lecture of geometrical optics, I'll illustrate you that how can we write the velocity of reflected ray when we are rotating the plane mirror and also keeping the incident ray fixed. Okay, now I've taken a plane mirror. You can see here, this is a plane mirror and there is a incident ray I. There is a normal n1 and the angle of incidence is I, this one. Now the reflected ray r1, this one, has equal angle with the normal, that is I, and also I've rotated the mirror by an angle theta in clockwise sense. You can see that I've rotated the mirror by an angle theta in clockwise sense, like this. And if I've rotated the mirror, then its normal will also rotate in the same sense by the same angle. Hence the normal will shift from n1 to n2 and the angle between these two normals will still be equal to this theta. Okay, now the new angle of incidence, as I've kept the incident ray to be fixed, the new angle of incidence is equal to I plus theta. You can see that this angle is equal to I plus theta, where the new angle of incidence is measured between the original incident ray and the new normal, this one n2. So this angle is I plus theta. Now obviously the new reflected angle, the incident angle has been changed from I to I plus theta. Therefore the reflected angle will also change and the new reflected angle will be equal to the new incident angle, that is equal to I plus theta. Okay, the new reflected angle will also be measured from n2 and this is the new reflected ray r2. So the angle between r2 and n2 is equal to I plus theta. Okay guys, now you can see that this angle, this is small angle between n2 and r1, this angle, I'll highlight this angle with color, this one. Okay, now this angle is equal to I minus theta. This angle is equal to I minus theta, and this angle is equal to I plus theta. So this angle will be equal to I plus theta minus I minus theta, and that will be equal to 2 theta. You can see. So there is a conclusion in this example that if the mirror has been rotated by an angle theta in the clockwise sense, then the reflected ray is also rotating in the same sense by twice angle 2 theta, although we have kept the incident ray to be fixed. So here is the conclusion. I am writing the conclusion that if a plane mirror is rotated by an angular velocity omega. Here you can see that I have derived the relation by angles and I am talking about angular velocity. We can conclude that if the mirror is rotated by an angle theta and the reflected ray rotates by an angle 2 theta in the same sense, then we can say that they both have rotated these angles in the same time. Hence if we differentiate their deviations, so we will get their angular velocities, and therefore we can say that if we rotate plane mirror by an angular velocity omega here, then the reflected ray will also rotate by an angular velocity 2 omega in the same sense of rotation. So this is the conclusion, and I'm reading out the conclusion once again, that if we rotate the plane mirror by an angular velocity omega, then keeping the incident ray fixed, then the reflected ray also rotates by an angular velocity 2 omega in the same sense. And again I am highlighting the axis of rotation, that the axis of rotation lies in the plane of the plane mirror, and the axis of rotation is being denoted by this cross because the axis of rotation is passing through this cross and it is perpendicular to the plane of this board, like it is coming towards you. So you can imagine an axis which is perpendicular to this board and which is passing through this cross. So the axis of rotation in my previous example and in this example is still the same. So I hope you understand the concept, and I'll be back with another concept of plane mirrors. Okay, thank you.